Right, we are at question 11. And this question tells us that we have 208 nucleons, right? And out of that 208, 82 are protons and 126 are neutrons. Right, find the electric field at the surface of the nucleus. Okay. So we are going to make some very bad assumptions, or rather the question makes you make those assumptions. Right, so simplify and make our life easier. So we assume that the volume of the nucleus is 208 that of an individual nucleon. Right, so that's what we get at first. Then we also assume that they are a sphere. Right, this is also an assumption. Once we get that, we can find that the radius is actually about 7 times that of a neutron. Okay? So that means you can pack 208 ping pong balls and you get a sphere that is 7 times the radius of a ping pong ball. There are obvious problems with that because when you pack spheres together, if they are non-compressible, you actually have a space between them. Here we are making the assumption that all the space gets squishy, is squished up, right? And there's no empty space between them. So once you do that, you can then again use this equation that we have introduced so many times from question 1 to 10. And then once we have this, we can remove the flux because flux is no longer a good useful consideration. Then we divide Q over E naught by the area. And we get this answer. Okay. Anyone got any answer that's different from this? Do I miss something out, is it?
Second line. 208 times 443,552.
Oh, okay. This one? Oh, yeah, okay, yes. But the value is still correct, yes? Okay. Yeah. Luckily, the number is still correct. If not, I would have made a terrible mistake. Right. Any issues with 11? So now let's look at 12. A piece of 10 gram styrofoam carries this charge and floats above the center of a large horizontal plastic sheet with a uniform charge density on its surface. So we're now talking about charged surfaces, plates in general. Okay. What is the charge per unit area on the plastic sheet? So F equals to QE. The F, the force on the styrofoam upwards, must be equals to its weight. The upward force is due to QE, right? The charge of the styrofoam itself multiplied by the electric field at the point of the styrofoam. Yes, this part, okay, Ken? This part doable? Any questions? So the electric field at the position of the styrofoam is then just the mass times the G divided by the charge of the styrofoam.
So then the question is charge per unit.
We are getting there. This charge here.
The final answer is
Oh yeah, the unit is wrong. What should the unit be? M minus 2. Should be correct, I think. Oh, so if you find any mistakes, right, please let me know. Okay. So then, the E field for a plate, we know this to be true from one of the examples we have done earlier. Example being page, example 6, right? So if you want, you can re-derive what I've highlighted here, or you could just use it. It's your choice. Then after you just start everything in, you get your answer. How many of you tried this question? You all get the same answer? Right? As long as got people get it, it should be correct, I think. Unless we made the same mistakes. So if you actually do this later on and you find mistakes, please let me know. Okay, I don't proclaim to be perfect, right? Yes, question?
No.
Okay. 13. Yes, cylindrical shell of this radius, a certain length of 2.4. So it's a very long, thin, well, not thin, long compared to its radius. Charge is uniformly distributed on its surface. The magnetic electric field 19 cm radially outwards from its axis is given by that value. Calculate the net charge on the shell and B, the electric field for 4 cm from the axis measured radially outwards. So again, you see, I keep using this equation, like nobody's recent, I keep using this. Then the flux becomes unimportant at some point. Why? Because I just bring E naught up, I get this equation. The area here is 2 pi r, should multiply by L, right? Did I miss out the L? Right? I should include L. So you then key in everything. Do you get this value?
Isn't Q over E not only for like one charge?
No.
The key is for any
Symmetric shapes.
What is
This is for symmetric shape? No, don't have to. Because Q over E naught is the flux. So even if it's a non-uniform distribution, it should still hold true. So good point out there. So this flux equals to Q over E naught, right? Need not be a uniform distribution. But this EA, we are using uniform, some kind of symmetric, right, idea about it, where the E field is the same at every point, right, at a certain distance around the cylinder. Right, because for the cylinder, every point it must point outwards. You get this answer? After you key in E naught, the E 2 pi R and L. Did you all try it at home and get this answer? Huh? Huh? You didn't get this answer?
I didn't get this answer either.
Okay. What's the answer? Maybe I did something wrong. What's the value of E naught? Did I put in the value of E naught somewhere? Electric field 36 0 times 10 power 3 times 2 times pi radius 0.19 meters times 2.4. No? Cannot.
This is what is it? Okay.
Is EA, this equation is Q. So Q is equals to E naught E times A.
Can you draw out the yeah.
So we have a cylinder like this. Right, the electric field at the midpoint of the shell, and the distance R equals to 19 cm. Wait. If I remove the 2.4, do you then get answer? Why is that correct? Oh, because it's because we're only considering this area, right? We're considering a slice of this and the E field through that surface. Right, so it's wrong to put in the L. Why is also this true? Why do we not consider the whole surface area? It's because, right? It's also because of this. If you were to consider a ring further down, the E field will not point perpendicularly outwards. This will be wrong. Because you have more charge above it than below it, the E field should point slightly downwards. Right, so if this is the cylinder, in the middle the E field will point outwards, but slightly down, right, the E field will point slightly downwards. Right, so it's not fair to use this for the whole thing. So you just consider for this. Well, that would be the charge. Fair point. Let me think about this. Okay, I'll give you all an email written reply when I think about this. Okay. Fair point. Part B, let's move on first. Part B. Part B is actually easier compared to Part A. If you get Part A, Part B is easy.
If the part A answer is correct.
Yes. I'll check this lah. Come back to you. Should be correct. Oops. Part B is easier lah. It's the same concept, just that E1A1 equals to E2A2. Then you get this straight away. Naturally, if you move closer in towards the object, you should get a larger value. Oh, wait, did I make a stupid mistake again? Sorry? Yeah, part B, I made a stupid mistake, right? Because I made the assumption that it encapsulates all of the charge, which is not. Because it has a radius of 7 and it's now 4 cm from the axis. Oh my god, sorry, I made a lot of mistakes here. So if you're looking from the top, 4 cm is inside, right? So you only need to consider a charge on the inside. Right? But wait, is it a shell? It's a shell. So there's nothing. So at 4 cm, what is it? What's the E field? 0. 0. My god, gonna trick. So, since, oops. Yep, since, nope, there is no charge within 4.0 cm radius, the issue. Such a
The thing only works if the thing is the shell is outside.
yeah. Yeah, it's a cylindrical shell, right?
So if it's beyond the shell, then
if it was, yes, if it was, so this equation, right? This equation that you have here, that I highlight, can only be used if it's, let's say from 19 cm, you move to like 8 cm. Because the charge it encompasses will be the same. Alright. 14. A particle with a charge of -60 placed at the center of a non-conducting spherical shell of inner radius 20 and outer radius 25 carries this charge density. The proton moves in the circular orbit just outside of the spherical shell. So you have a spherical shell that is not thin of a certain radius 25 and 20, and you have a proton, right, moves in circular orbit just outside. You can draw it like this. So that means I slice it down the middle, it should be moving like this. So it's moving in circular orbit first, you can tell that there must be centripetal force. So let's look first at how much charge it holds. So to find how much charge it holds, you have the charge per unit volume, so you must first find the total volume. So So total volume is given by 4 pi r cubed minus 4 pi r cubed. Yes? So you find the volume of charge. Yeah. Then you get the total charge by multiplying that in. And because at every point for a sphere, the E field always points perpendicular and it's the same at every point on the surface, right? So we can apply Gauss's law and this equation again. Then we can divide out by the area of the sphere. And we get 14743. Got this, Amanda? This E field first? No? Ah, okay. Oh, no. Then did I do something wrong?
So I got the final answer. I still got the final answer. 5.9575.
Yeah, I got the final answer.
Okay. Alright. So you get this E field on the surface, then F equals QE, and F equals mv squared over r circular motion. Then you sub in everything else, you get this final answer. Okay, 15. Consider a long cylindrical charge distribution, R with a density rho, of radius R with charge density rho. Find the electric field at a distance R where R is smaller than capital R. So again, we use this equation. But this is a tricky one, right? You are looking for, you have a long cylinder on not a thin shell, and you're trying to find, let's say, the electric field at this point. Right, so you need to draw a Gaussian surface and imagine it through the whole cylinder. So first, we must find the charge encapsulated by that surface. That means you imagine a smaller cylinder of radius small r within the big cylinder. So the charge will be the volume times the charge density. Volume will be pi r squared, the cross-sectional area, times the length of the object. So you get this as the charge. We're going to leave it there for now. Right? You're saying we don't know the value of L, right? Infinitely long, and if it's infinitely long, then what are you going to do, right? So forget that first, just leave it as L. Next, we're going to take the idea that E times A will give you Q over E naught. So you plug in the value of Q over there. And you realize that the L cancels out on both sides, which gives you the E field equals to this value away from the axis. Okay. So if you look at this answer, it means that the if you have this object, right, and you plot the E field, and it's a positive charge, the E field until the radius should be a straight line, right, and thereafter should be a 1 over R graph. Yes? (16) Thin spherical shell, 40 cm, total charge distribute on its surface again. And now this one definitely part A 0 because thin spherical shell, no charge inside, 0. Part B, 20 cm. So part B is a repeat. So question 16 is like a repeat of a lot of the things that we learned until now. Do you all get this answer? I look at you, yes. Because you are the one that has done the thing. Thank you. The rest of you, you have not tried it out yet. Okay, so try it out. Then you can understand the pain of trying it out. 17. Insulating sphere of radius A and has a uniform charge density with total charge Q. A spherical Gaussian surface R which shares a common center with the insulating sphere is inflated starting from R. That means you imagine the surface to slowly grow like a balloon. Find expression for the electric flux passing through the Gaussian surface for R smaller than A. So it's a solid sphere, not a shell. So you define the charge within the sphere. Right? So first, let the charge density be rho, and rho will then be the charge, total charge Q divided by the volume, and the volume is a fixed value because the radius is A. So the encapsulated charge must then be rho times the volume at whichever radius. So this is the volume at whichever radius R. Right? So it's a ratio of volumes. So essentially it's just Q R cubed over A cubed. Right? Am I right? Yeah, okay. Which means that the flux is Q over E naught, QR cubed over A cubed, and divided by E naught. I sub in the Q, small q, from what I've done. And notice how I do it. I do it step by step. To find Q first, I make my steps easy. Which means, if I have a sphere, and I plot the E field versus distance, as R increases, it increases, not as a straight line, but as a curve. And once it goes outside, the E field is given by 1 over R squared. So this is an R cubed curve. And once outside, it's a 1 over R squared, right? The E field. Yes? No, we're looking for flux. Oh, sorry, flux. Oops. So if it's flux, then it's a different picture. Yeah, I confused it. Flux is just a... Because afterwards, the flux must stay the same. No, right. If I ask you to find the E field, can find or not? Also can find, right? How would you plot the E versus R? think the E field, EA, right, equals to U over E naught. And you remove the others. And E is just Q R cubed over E naught A cubed times the area of the sphere is 4 pi R squared. So your R actually goes away, right? And you essentially have E proportional to R. So if you have the E versus R graph, yet again, it is a straight line, and then 1 over R squared outside. Okay, so it's proportional to R. Look very similar, right? But this is 1 over R. I'm doing an exhaustive tutorial. That exhaustive not just being tiring, but I try to cover all the questions. Now you know why the word came. It was an exhaustive search, meaning complete. 18. I gave you 20 plus questions, yes? We need to quickly get to the hard ones. Can we skip this? Is this easy enough? Shit, okay. So I will leave 18 and 19 for you to read. I'll email this to you. It should be, it's similar, right? It's a straight filament wire, uncharged cardboard cylinder, surrounds the filament, find the field at the surface of the cylinder, flux through the cylinder, yeah.
So how many got Weber?
Flux is Weber, right?
Oh.
The units of flux is Weber, isn't it?
So magnetic flux and electric flux.
Magnetic flux. Is it? Oh, yeah, sorry, it's not, right? Weber is for magnetic flux, right? Sorry, I'm so confused. What's the unit here?
Newton meter square per
Newton meter square. Okay, I just use yours. Hey, what happened to you? Okay. How do you go? Okay, well done then. Hey.
Good job.
Are you afraid? I said that.
Okay, 19 for a flat horizontal charge. Calculate if you just above the middle of the sheet. So this is the direct application of example 6, right? Just plug in the numbers, you get your answer. Okay? Any issues with this? You all really must try during the June holidays. You just do your H2 and forget about H3. Gauss's law for magnetic fields, we are Mr. Dr. Goh will cover this, but this is the one I gave you. Basically, it's just this kind of answer. Generally, right, if you have Gauss's law, I just give you a teaser that what he will teach. Generally, you will always find that the flux will always be 0 because there are no magnetic monopoles. Okay, so you see Gauss's law for magnetic fields, the answer is typically flux 0. If you have flux non-zero, then you have found monopoles. Ampere's law, we are skipping. This is the one I showed you that was like multiple pages. And then we can talk about, is it this? No, not this. This is the one, right? My question and your question is a little bit different. What's your number here? $21, right? Okay, so these are 21, Wait, let me. Let's save this separately. Save as. Okay, then let me remove all the irrelevant ones, then you have no issue. And this monstrous one. This is the one that's 3 pages long that I showed you all last time. Okay, take that afterwards. Okay, come back.
Are you going to play?
Okay, 21. Electric dipole of this, I want to cover a few that's particularly important because you won't see anywhere else. But let's do a bit of dipole moment and dipole energy first. The magnitude of the dipole moment is given by P equals to 2AQ. So you submit everything, you get your answer. Okay? The one about the potential energy, when it's parallel to the field is 0. When it's perpendicular, it will be non-zero. Whether it's up or down doesn't matter. So this is the field. If your dipole moment is like that, that means you're positive on top, and the negative is below. Right? That is not good. Sorry. Yeah, if you're like that, if your dipole moment is like this, you're positive on top, your negative one is below. Okay. Any questions for 21? Can? Can? As long you not means is correct. 22. Same thing. Same thing. They say what is the torque. So torque here is P cross E or PE sine theta. I always write both down, right, to make my life easier so I remember both. So in parallel, theta is 0 degrees, so sine 0 is 0, so the torque is 0. Does it make sense? Right, when it's parallel, there's no torque. Right, it's in the most comfortable position that the dipole moment wants to be. When it's 90 degrees, the torque is then maximum. So 21 and 22 are the foundation, right? One talks about dipole moment and the energy in 21, and in 22 I talk about the torque. So these three are the three things that I can ask: moment, torque, and energy. Okay? When you're anti-parallel, the torque is also surprisingly 0, but it's a unstable equilibrium. Question 23. How much work is required to turn it in a uniform field? So again, we apply this equation. So this is a direct application of the equation. Just hard whack can already. Did I do something crazy here? Yes, I did. 23 degrees, right? No, 203. Did I do something wrong? It's 203, yeah? I thought I did something wrong. Okay. So initially, angle is 23. And you're going to turn 180 degrees. Okay. So let's draw it up. Sometimes the picture speaks 1,000 words. Okay, so initially, the positive is here, negative is here, and it's 23 degrees from the E field. Then you want 180 degrees, which is like this. where the positive is here. Hey, what am I doing?
Why do you multiply the charge by
22b. Let me take a look. You have 2e, right? Right, and the equation 2aq, the q is a q of one of the charges, right? Correct? Huh? I mean, I tend to make weird mistakes. So if you see any, please let me. 23, is it okay? I want to quickly talk about 24 and 25 because those are the ones that I'm sure you all are going crazy about. Provided you reach those questions. Alright, any issues? See? 24, finally, we can talk about the crazy one. There you go, one page. Right? So let's do it. You are trying to find what happens when you tweak it slightly. And for those of you who were actually in my physics class when we played the magnets, remember we placed a coin and the coin lay like that? And some of you actually started to, the coin was, it started to like vibrate. It started to vibrate the coin and the coin, right? So that was a bit of some kind of harmonic motion. But we're going to prove that this is actually, in this case, when you vibrate it, when you shift it a little bit, it's going to rotate as an SHM. Right? How are you going to do that? So first, we know torque to be that value, right? That equation. So torque equals to P sine theta, where is the momentum, or rather the dipole moment, sorry, times the E field is in times the angle that it was rotated across. Dipole moment dipole moment is 2aq, the distance times the charge. Okay. Then we learn from moment of inertia this equation. If you don't know this equation, please don't ask me. I'm not the expert in this. But you have this equation, yes? So when for small angles, this becomes, right? So then you can compare the two equations together. So you get PE equals to negative L squared E squared theta. You rearrange this monster, you get,
It's not I.
is I, I. Moment of inertia, yes, sorry. So if you rearrange this monster, you get negative PE theta over I equals to d square theta dt squared. Now this looks awfully similar to what you have in SHM, right? Awfully similar. Compare the two equations. Yes? Where your x is theta Yeah? So you can then conclude. You can, trust me, you can. Because for small angle, the angle is proportional to the displacement. For small angle, the x displaced here is proportional to theta for small angles. That one is true, so you can conclude that. So you can conclude then that the omega is P E over I.
Right, what is the McCallum figure? The small angle. Yes. The sine is there.
You mean this one? This one you should know lah. This one we have been using in H2 lah. No, if you rotate bigger than a few degrees is probably not as much. Definitely not. Then, ta-da, you have the answer. The frequency is just this. Wow, so easily solved. So there's actually three crazy concepts here. One, from this chapter. This is from Mr. Stan's chapter. And then you need to apply your H2 concept on a non-usual equation sequence. And you get this. just 3 topics.
Where's the negative sign of from? What in top is negative I squared equal to E squared?
Isn't it not like this? It's a compensating.
Is it how there's a negative sign? How where it comes from?
What's always supposed to have motion direction?
This one, oh, go ahead, ask Mr. Tan. I think it should be true. I believe that to be true. Okay, so the thing with this is that this is actually a classic question. Very classic. So, being the first year of H3, this may be something that they would like to test because you have moment of inertia. So hard memorize. If you don't know, just memorize. Okay? You have moment of inertia, you have SHM, and you have. So I'm trying to like spot questions lah. Okay, so this is the one I thought quite classic, and happens to be across topic. So very nicely in the H3 spirit of H3.
What do you mean top? How do you know to use top? And how do you know to connect every top?
Is this? I don't know. It's just how it is solved. How else would you do it? How else would you do it? I don't know. I mean this.
I did it by taking
Oh,
I d squared theta as I alpha naught. Then from there use SHM. And then when alpha naught equals to when A equals to alpha naught.
you get the same results. Because in the end, you also must compare with SHM, right?
Yeah.
At some point, you must bridge between angle and displacement being the same to get SHM.
Can we sin theta equals to x over half the dipole?
Can. And for small angles, then is proportional.
So is it we use top right from the moment of inertia chapter because it's rotational?
Yes. Okay, so this is the one that I thought the answer doesn't come through repetition. This is you need a moment of eureka then can get, yeah. So this kind of question you'll probably see it once, the next time you come you can still do it. Right. So you just need to get the eureka moment once. 25 is it's not so nice one. We use vectorial method. Again, very common in the universally text, right? We always give you simple angles, but then suddenly they hop into a different way to represent the directions, and then a lot of students don't know how to do. I faced the same problem when I was a student. I assure you, you use the same methods, and this is just the vectorial method. So if your math is very, very strong, this is actually right up your alley. Because it's just representing all this in a vectorial form. Okay, so if we want to draw it up, we can. right? You have a positive charge, negative x at 1.2, and the y is 1.4, and that's where your positive charge is. The negative charge is at 1.5 and negative 1.3. Right, and this is where it is. So the P dipole moment points this way. Okay? The electric field has, this is your I direction, this is your J direction. Right, so I, J, and Z is up. I, J, K is up. So you have 7, 8 in this direction and negative. So your E field is slightly in this direction, if I'm not wrong. It's more I than J. So you naturally have an angle theta here. So if you want, you can convert the vectors that they have into what we are used to in the previous parts. You can. Right? You can actually then try to find the angle below the dip here, you can try to find the angle here, then you can find the angle in between. You can. Not stopping you. Okay? So if you refuse the vectorial method, you can. But if you don't, you can just do this mechanically. Then meaning I can set a question where I change the numbers. You don't need to know the physics. Just sub in these algorithms, right? You are done. The answer is exactly the same. As in, the answer won't be exactly the same. The method is exactly the same. So this is just in case they give you this kind of vectors, instead of taking time to repurpose all the angles, you can just whack the algorithm. So this one you need a bit of hard work and hard memorization. Yep. So everything else is the same. Okay?
The maximum potential energy is when it's opposite to the electric field.
Yes. Where does the top point? In the Z direction, right? In fact, in the negative Z direction, so it actually points into the pitch. Right? P cross E points into the pitch is correct. Right? So you see the vectorial method, don't even need to know what cause, just solve, we get an answer negative points away. So I try to bridge what we've been doing with the vectorial. Okay, Ken? And that's it. Done. I'll send you the answers.